All right. So now, let's just make a following point that this maybe sounds silly, but just talking about this is meant to help clear up a little bit more what surface integrals, not only what they're good for, or what they could be good for, and there's many possibilities, but that this will also, I hope, clarify a little bit more what surface integration is, like what it what's really going on mathematically. So if this shape here is a rho, it's the Greek. It looks kind of like a rounded P, but it makes the sound of an R. So if rho of x comma y comma z, let's say that this gives or defines the density of an object at the point x comma y comma z, then the double integral of rho of x comma y comma z over the surface capital S d capital S, this gives mass, right? How heavy something is. So let's just clear up what we mean by density first by saying this. If at the point, so you have an object, maybe I guess a rather large object because there's going to be a point 82 comma 82 comma 82. If at the point 82 comma 2 comma 82 comma 82, if this point is occupied, what am I trying to get at with density? Okay, this point is occupied by lead, and let's say the point 3 comma 1 comma 4 is occupied by pi, then you should really end up, if I understand correctly, then we should end up with rho of 82 comma 82 comma 82 is a much larger number. So not just greater, but really greater than rho of 3 comma 1 comma 4. That is, if you have 1 cubic centimeter of lead versus 1 cubic centimeter of blueberry pie, shouldn't the cubic centimeter of lead be much heavier? So what I'd like to do then is basically follow up with the previous question, where we were looking at a parallelogram, and do the following. So you could have an object. Basically, why have a density function? The idea is you could have an object that's made up of many different materials. And so, at one location, made out of plastic, the thing is not as heavy, and then made out of metal somewhere else, the object is much heavier. And so we're trying to simulate that with just saying, oh, there's a function provided that lets you know the density. So if the density at each point in the parallelogram from just above in the previous example is given by rho of x comma y comma z is equal to, let's just say x squared times z, then what is the mass of the parallelogram? Again, we're just reusing the work that we had earlier, just so that we don't have to work so much. Whoops. So to answer this, we're actually going to borrow some things from up here. Specifically, we had already computed, we had already computed a parameterization and saw a parameter domain and all that business. Okay, so we're just going to borrow all that stuff in the red box up there. So our answer is actually going to be very much like what we have. Maybe I'll box this in another color as well. How about our answer will look very much like what we had here, just really with a different function. So we're going to have that this should equal integral. So let's just write it both ways here. So integral over s of rho ds, and this is going to equal integral 0 to 1. Integral u also goes from 0 to 1. Let's see, x squared z, So x gets replaced with 1 plus 2u plus 3v. Okay, that's from up here, squared. And then we have z, which gets replaced with this right there. So quantity 5 plus 6u minus 2v. And then we need to just end with the magnitude of the cross product times a du dv. So we'll have a root 2 squared plus 22 squared plus 14 squared, and then du dv. Okay, so we borrowed a lot of the work from earlier just to save a little bit of time, and we'll just say really what's going on when computing mass using a given density is that rho just plays the role of this f of x comma y comma z function. That's all. Okay, in computing double integral over s of f of x comma y comma z d capital S. Now, recall that if capital S is the surface given by the graph z equals lowercase g of x comma y. So we've used a g because we're using an f as a function we're integrating. But so let's say you have a surface that's just the graph of a function, right? So graph of a two-input function. By that, I hope you get what I mean, two-input variable function. We had earlier seen that the area of, let's clean that up, function. We had earlier seen that the area of this surface was given by the double integral over capital D of root 1 plus partial derivative of g with respect to x squared plus partial derivative of g with respect to y squared dA. This is just really created from the more general version. So it's just a special case, but it's a useful special case. Here, capital S, just to clarify what the region was. This was actually all points of the form x comma y comma g of x comma y, belonging to three-dimensional space, so R3, where x comma y runs through all points capital D in the parameter domain. So apologies for this notation if you're not as familiar with it, but you just go through each x comma y that belongs to capital D, and then you create a point in three-dimensional space, which is x comma y comma g of x comma y. So if capital S is given by the graph of a two-input function g of x comma y, we now want to, just like we did with the other way that a surface is described, just purely parametrically, we now also want to describe what the integral of what a surface integral in general looks like, given a function lowercase f. So this, I hope, won't be too surprising that the double integral over a surface like this of f comma x comma y comma z d capital S, it will be the double integral over d of f of x comma y comma g of x comma y times root, copying from above, root 1 plus partial derivative of g with respect to x squared plus partial derivative of g with respect to y squared dA. What's important to point out is that, remember, x and y are just parameters. They were just playing the roles of the parametric variables, or the parameters, instead of u and v, right? So x and y are just the parameters. So we replace, in a sense, x with x and replace y with y. So in other words, really no replacement is needed. And then for that reason, this dA is dx dy, or is going to end up being dy dx. The only real work to do is right here, is that z gets replaced with g of x comma y. So it's really everything that should happen based on the fact that the parameterization just uses x and y. And if you want to go back to that, the parametric version of surfaces, this really all works out. Just one other comment we should make here is that if capital S, and that's actually this S here, is, yeah, let's say it this way. Let's organize this better. If capital S, that's this S, is the graph of g of x comma y, then ds, d capital S, is just notation, so that thingy here is equal to root 1 plus partial derivative of g with respect to x squared plus partial derivative of g with respect to y squared dA. So the key thing about this substitution that occurs right here, let's kind of point this out, this right here, the whole key deal that's going to make this work in this setup, in this format, please note that the dA integral, that is this integral right here, should be all in terms of x's and y's. No z's. Okay, all the z's need to get replaced with g of x comma y. So let's do an example. So let g of x comma y equal 10x to the fourth y to the sixth. And what is the integral of f of x comma y comma z equals the fraction x minus z over y squared plus z for 1 less than or equal to x less than or equal to 5 and 2 less than or equal to y less than or equal to 8. So since we're talking about let's clarify a little more. This language is a little vague. Okay, so let's just say, what is the integral of f equals that fraction? Okay, so there's a function f over the surface, capital S, given by z is equal to g of x comma y for 1 less than or equal to x less than or equal to 5 and 2 less than or equal to y less than or equal to 8. Okay, that makes things clearer. So because we can just use x and y as the parameters instead of switching to u's and v's, or if you switch to parametric, it's just x is u and y is v, then our parameter domain, we can just go with all x values between 1 and 5, Cartesian product all y values between 2 and 8. Then d capital S, based on what we see right here, should just be equal to, well, root 1 plus, now we need the partial derivative of g with respect to x. So take a look over here. Yeah, we'll have 40 x to the third, y to the sixth, okay, that quantity squared, plus now we need partial derivative of g with respect to y. So that's going to be 60 x to the fourth, y to the fifth, okay, that quantity is squared, okay, and then dA. That dA could be for us dx dy or dy dx. We'll just go ahead and go with a dx dy. We don't have to overthink this because our parameter domain in this example is just a rectangle. Okay, so then the integral, the double integral over s of the function f, so x minus z over y squared plus z d capital S. Okay, this thingy, let's clean this up here. So this thingy here, the fraction being, of course, capital lowercase f, this is going to get this is going to become, so we need an integral over d, and this will be integral, let's see, if it's dx dy, then y is on the outside, so y going from 2 to 8, integral x going from 1 to 5. Now we need to replace, so we've got to do this, thingy that's right here. Oh, I'm running out of colors. How about this? We need to do this. Yeah, we need f of x comma y comma g of x comma y. Now, so that means in what we see here, every x gets replaced with x, every y gets replaced with y, and every z gets replaced with g of x comma y. So every z needs to get replaced with 10x to the fourth y to the sixth. So let's do that. Yeah. So in this space here, we should have x gets replaced with x, okay, minus z gets replaced with 10x to the fourth y to the sixth. This is all over y squared, y gets replaced with y, plus z gets replaced with 10x to the fourth y to the sixth. Okay, so what's in this red box is meant to be the specific version of what we saw up there in the formula. Let me just point out again, well, let's do that at the end of this. Okay, so then we need this part. We had actually already computed that ds that's right here, so we just need to copy this down here. Root 1 plus quantity 40x cubed y to the sixth squared plus quantity 60x to the fourth y to the fifth close parentheses squared dx dy. Okay, let's consider ourselves done with the problem, but if we go back and look at this integral, you'll notice that we replaced the z's that appeared with 10x to the fourth y to the sixth here and there. If we did not make that replacement, then this integral here would have z's floating around in it, but it's just an integral with respect to x and then with respect to y. So that would be messy. There'd be 3 variables but 2 integrals. So this is what we mean earlier over here, that z gets replaced. And if you don't do that replacement, okay, then you're going to have a problem. The dA integral should all be in terms of x and y, no more z's. So that's why we had to replace these right here.